All right, up to now we've taken a look at the choose number, right, using Pascal's triangle. Now that kind of, so what that was, if I had n objects, I choose k of them, right? So we thought of this as different sets, right? Since the ordering didn't really matter, all right? But what if I change the problem a bit, and instead I do actually care about the order, right? So if I had n objects, right, how many different, in this case, not a set, but sequences can I have? Right, so for example, let's say we had the letters A, B, C, and D. Right, so here, right, I want to determine how many sequences I have here, or orderings of the letters A, B, C, and D, right? So now we can visualize this here. If we say, okay, well, in the first position, right, I have 4 choices. Right, I can start with A, start with B, I can start with C, I can start with D. All right, now as I increase it for the second one, now notice each of those letters branches off for the different options, right? What's left, right? If I start with A, then again, here we're assuming no repeats, right? We're not repeating here, right? We'll discuss the problem of, well, what if I allow repeats later? But for now, we'll keep it simple. We have these n objects without repeats. And how many ways can I order them, right? Not a set, I don't want to choose sets, which again, sets are unordered, but here more of a sequence. So we see that these branch off, right? A, B, C. Now as I go one more here, we see those branch off here, right? Because once I go from A, B, then I have 2 other choices, right? C or D, right? A, C, that leads to B or D. All right, and then lastly, once you've made those choices here, and there's really just one, the last one, there's no choice, right? It's just whatever is left over there, right? And then we can see, we can count these up here, right? Now notice here, we have kind of similar to the product principle here, right? It's not 4 to the 4th here. Right? What we have here is we initially have 4 choices, and then after that, these branch off to 3, right? 3, 3, 3, 3. Right? And then from there, 2, 2 branch. Each one of those branches off into 2. And then lastly, 1, right? Because there's only 1 left there. And as you can see here, we should get 24, right? So what happens here is, the way you want to think about this is for permutations, right? We start off where, for this particular example, right, our first choice, right, there's 4 of them. Then after that, once you made that initial choice, then the next choice, you have 1 less to choose from. So we have 3. And then again from there, 2. And then lastly, whatever's left over, 1 for the last one here. So this is what is called a permutation. So a permutation is an ordered arrangement. Ordered arrangement of objects. Okay, so the number of ways to arrange, if we have n distinct objects, as you can see here, right, this value is 4 factorial, and we can kind of generalize here, right? That would be n factorial, where n, right, the product principle each step of the way, n minus 1, n minus 2, etc., until I get to 2 times 1. Okay, so we can think of, right, how many choices we have at this particular slot, and then at each step of the way we have one less choice. Okay, so here, if we wanted to have an arrangement here, let's say for this example, here we have 6 students line up for a photo. How many different permutations are there of the 6 students? Okay, so let's say, so that would be 6 factorial, right? If we think, right here we have 6. Right, so if we're lining them up, right, the order is going to matter, right? So we're sequencing the students here. So in that first position, there are 6 objects here. Then after that, we have 5. And then 4, and 3, 2, 1, which I believe is 720. All right. Okay. All right. Now, one thing to moving forward here that we'll use as a convention here, 0 factorial is going to be 1. Okay. So we'll just define that here. It simplifies all of our theorems and counting moving forward here. Okay, so again, if we want to determine how to arrange n distinct objects, then that is just going to be n factorial. Now, what if I don't want to arrange all of them, right? What if I do have n distinct objects? Right, so I'll have k permutations of n distinct objects. So I only want to arrange k of them of the n, not all of them, right? So for example, let's say how many string of 4 letters and again no repeats from letters A through G. Okay, so here we have 7 objects here, the letters. But I only want to arrange 4 of them. Right, so here our arrangement again is ordered. Right, string of 4 letters. So again, the way we think of this is here we have 7 choices for the first slot. Then after that, we only have 6, then 5, then 4. Okay. All right, which again, doing that multiplication, we get 840. All right, so 840 different string of 4 letters from the letters A through G. Now, here, let's kind of see if we can think of a formula for this, right? Now, it's not quite n factorial. It stops short here, right? But the way I can think of this is, well, in terms of factorials is, right? Well, I can use 7 factorial, but this is going to be too much, right? That's too big of a number here, right? But if we notice here, what is missing from the 7 factorial? It's the rest of the permutation. So what I can do is I can just divide it out, right? Or you can think of this as 7 factorial, 7 minus 4 factorial. Okay. All right, and as you can see here, right, as expanding that out, kind of working with the factorials, you could see why this makes sense, right? Because then you could expand the top to this part here, and then you're left with times 3 factorial, and that reduces to 1, right? So as it turns out, our formula here, so we use this symbol. So with this, or this notation here, right? P is permutation, so the permutations of n distinct objects of length k, right? So that formula is n factorial over n minus k factorial, right? And that simplifies to n minus 1, all the way to n minus k plus 1. All right, just right before that n minus k part. Okay, so for example, let's say I had 10 distinct objects. How many permutations of length 4 are there? Okay, so again, it's this P n k, where n is the total object, so here 10, and then k is the length of the permutation. So in this case 4. So again, plugging it now into my formula that I have, that's 10 times 9 times 8 times 7. Actually, let me just work it out here. So we would have 10 factorial over 10 minus 4 factorial, which is 6. So we're left with 10 times 9 times 8 times 7, which is 5,040. Right. Okay. All right, so again, this P and K counts ordered arrangements, so sequences with no repeats. All right, what if only, so the next thing we're going to take a look at is what if only the selection matters, right? Not the arrangement, right? And we'll get more into that, right? So again, when we are thinking of, now we've introduced this part of the permutations as opposed to the choose, right? You want to think of it as the two different objects that you're kind of creating, right? When dealing with the choose number, right, that was more like sets that you're choosing, right? Sets of size k from n distinct objects. And here we're ordering, right? So it's more of a sequence. So order matters here, right? But think of it as sequence, right? It's not the only thing we're looking at, so just something to keep in mind here, right? But we think of it more as the sequencing of these objects here.